we are going to be hearing from Avik Basu, who is a data scientist and software engineer on causal machine learning.
All right. OK, loud and clear? Cool. Yeah, hey, everyone. I hope you're doing well. This is probably the last talk of today, I think. Yes. OK. So I hope you guys are not too tired. This always happens to me, but it's fine. So today I'm going to talk about causal thinking in machine learning. And now this is something, full disclosure, this is something new to me as well. But it's something that I have gained real interest lately. So we'll dig into some concepts together and see how that goes, right? So a little bit about me. I'm based in the Bay Area. I am a data scientist at Intuit. I actually call myself a full stack data scientist because I kind of do the whole thing, the whole pipeline. I'm also an editor at PyOpenSci, which is a nonprofit for broadening the acceptance of scientific Python packages. And I come from, as I said, both an engineering and a data science background. I'm an avid gamer, so I love PS5 and Steam Deck. For some reason, I forgot my Steam Deck. I don't know why, but I'm not very happy about that. I love tennis and soccer as well. But yeah, I play tennis. I just love it. And then driving is something that I feel is very therapeutic, given some conditions are met. Conditions like these. Miata is always the answer for me. So yeah, OK. The best condition is that it has to be a stick shift. It has to be a rear-wheel drive. And it has to be lightweight. So with that, let's move forward. So the agenda for today is that, and really the goal of today's talk is to give you an intuition behind causal thinking and how you can use it for your own use case. So we'll go over the correlation versus causation, the classic concept, and then some concepts which are very specific to causal inference, and then we'll talk about uplift modeling, and finally we'll go through evaluation and some of the key takeaways. So let me start with a scenario many of you have probably encountered, okay? And it's basically this, okay? We build a model to predict customer churn, okay? And it's got a great F1 score of 0.9, and you're feeling good about it. And you can see that the model learned that probability of churn given call support is 0.45, and the probability of churn given no call is 0.15. Okay. Now, given this, you're very confident about this pattern, right? So you can actually have an insight that customers who call support are 3x more likely to churn, right? Someone from business team says that, great, how about we reduce the support calls to prevent churn, right? And this is where we need to pause, because our model can be 90% accurate, but still lead to completely wrong business results, okay? So the question we need to really ask ourselves is that, did support calls cause churn, or did unhappy customers call support, okay? So this is the classic example of correlation versus causation there, right? So the key insight here is that high accuracy does not really translate to an actionable insight there, okay? So now let's talk about or in other words, let's just formalize the distinction between them, right? So we have the predictive models where it estimates expectation of y given x, okay? And it answers the question, who will buy? And the answer, and it also answers, what is going to happen, okay? So who will buy and what's going to happen? And in case of the causal model, you have a different kind of a whole thinking, basically. So you're actually estimating what is the uplift. The uplift meaning that what is the expectation of y given that there is a treatment minus of y given that there is not a treatment. We'll actually go into these notations later on, but that's just to give the basic idea. And the question is that who will buy because of the treatment, okay? And the answer that we are trying to look is that what is the effect of our action. So as you can see that these are fundamentally different questions requiring different approaches, right? So let's go through this problem, and we'll actually go through this same problem over and over in this talk. So let's just get this very clear, right? So we take a concrete example, and in this, that you run an email marketing campaign and want to really measure its effectiveness. Okay, so you have a prediction model, and this prediction model basically says that 20% of customers who got emails purchased. Okay, but this is just an observation, by the way, right? And then in the intervention, you have something like, okay, sending the email increases the purchase rate by 5%. Okay, that's the actual effect of the intervention. So you can see that the expectation of purchase given t equals 1, which means the email is sent, minus expectation of purchase given that it's the control, which means no email is sent, is 0.005, okay, which means that sending email increases the purchase rate by 5%. So same data, but we're asking some different questions here, right? So now here's your campaign results, right? So you have your received email, which is the treatment group, and the purchase rate is 20%. No email, you have the control group, where the purchase rate is 8%, right? So it's a simple math. Email boosts purchases by 12 percentage points, and we are just ready to ship it, right? That's what I would actually vote for, right? So email boosts purchases by 12%, so let's just ship it. Well, not so fast, because we need to really figure out who got the emails in the first place, right? So the problem is that your marketing team was not sending these emails randomly. They actually targeted customers who were recently active and people with very high engagement history. Okay, so that 12% difference that we saw, it's not actually from that email that you sent. Okay, because some of it is that engaged customers are going to buy more anyway. So the problem here is that that the observed 12% difference is actually some true effect. It is there, no doubt about it. But then there is also a big amount of selection bias that we need to really subtract to get the true effect. So the true effect is what we want. So let's look at the real picture of the selection bias. Okay, so now we actually break it down by the customer type. So here you can see that the high engagement and the low engagement are actually features. So you can think of it as a feature to your model, right? And let's just focus by each customer type. So if you look at the high engagement, so the people who received the email, they actually did 20% purchase. And then the no email group, which is the control, they did 16%. So the true effect of the high engagement is actually 4% if you subtract the two, right? And the same, and a similar goes for the low engagement as well. It's 6% for the treatment group, and then the 3% for the no email group, right? So it is actually 3%. So here one thing to really think about is that the customer engagement feature is actually a confounder. It affects both who gets the treatment, or who gets the email in this case, and who purchases. So it affects both the target variable and also the treatment variable. All right. So I mean, how do we really solve this problem? Well, the best way to do that, or I would say the gold standard of this, is randomized control trials, right? Or some randomized A/B tests. So the key idea is that it just ensures that treatment and control groups are identical at the baseline. So we're not going to do the same mistake that the marketing team did last time, right? That we need to make sure that we assign these things randomly, right? So what really happens after randomization is that the treatment group, well, random 50% of all customers. The control group, the same thing. Now, when groups are identical on average, we can really see the true effect. Okay, so any difference we observe is actually the true effect of the email, right? So randomization breaks the link between the customer characteristics and the treatment assignment. So, but what is the problem then? Well, the problem is that A/B tests are really expensive, and depending on the industry you are, it can be very unethical as well. Okay, they also take much more time to run. I mean, by unethical, you mean, you can't just randomize medical treatments, right? And often we've already collected the data as well. So the campaign already has happened. Now we need to make use of that data as well. So what do we do? Well, first thing is that we need to ask this question, that how do we estimate treatment effects from observational data, okay? And this is where uplift modeling really comes in, okay? So there are actually 3 components of uplift modeling that we need to really take care of. The first thing is the potential outcomes, how to think about treatment effects, right? So there are some distinctions that we should really know about when we think about that. The second one is conditional average treatment effects, or CAT, CAT, where we are trying to so this is exactly what we are trying to estimate here, okay? And then the third part is the meta learners, is actually the how. How do we estimate the conditional average treatment effects? So let's just dive right into the potential outcomes framework. So this is really about a framework for thinking about treatment effects. The idea is pretty simple, but actually powerful, right? So what do we do? For each individual, and this comes to the notation that I was referring to earlier, there are actually 2 potential outcomes, okay? Y of 0, okay, for a person I, right, which is that they are not treated, which is they're in the control group. Y of 1, okay, of a person I, which is that outcome of a person if treated. So both of these are Y, as you can see. So this is actually the target variable, or the outcome. The superscript 0 and 1, they are actually the treatments that you're giving them, okay? So the individual treatment effect, okay, is simply the difference, which is Y1 minus Y0. That's all, okay? An individual treatment effect is really what we are looking into, meaning that in an ideal world, this is what we need, right? On an individual level, how much of a lift are we getting by assigning the treatment, or by intervening with any kind of treatment, right? So that's more about it. But here's the problem. We can never observe both outcomes for the same person, okay? So let's take an example. So Maria got an email, T equals 1, and did a purchase, Y equals 1, okay? Very clear. So it's very clear that we observe Y of 1 equals 1, because she got a treatment, right? But we do not observe Y of 0. Why? Because that thing never happened, right? So that is known as the counterfactual, okay? So we can't really rewind time and try another scenario. I mean, I don't know if you know that, but I don't know, okay? Right, but we cannot really answer this question, that would she have purchased without the email, right? And well, if she did, well, now you can see that Y of 0 equals 1, meaning that she purchased it anyway. In that case, our individual treatment effect is actually 0, because nothing changed. I mean, she would have bought it anyway. But if it's 0, Y of 0 equals 0, which means that there was some lift. There was some lift because the email caused the purchase there, right? So that's about that example, and this is a key distinction that we need to really remember, right? So the motivation, I mean, why all of this, why does all of this matter, right? So just like these 2 people respond completely different to olives, okay? One loves it, one hates it, right? Individuals respond differently to interventions. And if you look at the average treatment effect, we might see 0 and conclude that the intervention does not work, but that could not be any far from the truth, right? So the goal is to provide intervention to the right customers, and I'll go into the details, right? Individuals respond differently to interventions, and as I said, if you just sum everything over, the average treatment effect might be 0, but that's not what we're looking at. So in fact, there are actually 4 distinct types of customers, okay, or 4 distinct types of people. Let me show you how this hypothetical scenario, where we can see both potential outcomes. Okay, this is not real. This cannot happen. But let's just imagine that we can see both potential outcomes. Okay, so we have the first customer, Mr. Grayson. Okay, and he is basically, you can see that 1 means that that person purchased. 0 means that they did not purchase. Right? They received an email, and Mr. Grayson did purchase. No email. Well, he purchased then as well. So the ITE is actually 0. So this is a customer who is a sure thing, meaning that they would buy anyway, Mr. Drake, where well, he received an email, and he did purchase, but with no email, he did not purchase. So the ITE is 1, and this person is a persuadable, right? Then we have Ms. Gordon, who, when received an email, did not purchase. With no email, did not purchase. So this person is a lost cause, right? I mean, this person is not going to buy anyway, right? Then we have Ms. Kyle, who received an email, did not purchase. But when there is no email, did purchase. So you can see that the ITE is actually negative here. So this person is a sleeping dog, right? And if you notice, the average treatment effect here is 0. But that's not truly the full picture, right? A side note, does anybody realize what these names are? Yeah. OK. Great. Batman. So Mr. Grayson is Nightwing, Mr. Drake is Robin, Miss Gordon is Batgirl, and Miss Kyle is Catwoman. OK. OK. So persuadables are the ones that we really care about. They have a positive treatment effect, right? Because they convert because of the intervention. So now this is one thing to note. A traditional ML model will just predict P of y given t equals 1 and x, right? So the probability of someone will convert if treated. So ML models actually target the sure things and the persuadables, right? But we are looking to identify just the persuadables there, okay? But here's the fundamental problem. As I talked about, that was a hypothetical scenario. Here, we never observe these potential outcomes, right? So every person is either treated or not treated. We can't see both. We can't directly compute ITE for everyone. We got 2 new names. I'm sure you guys know who them are. OK. So now let's talk about, so if we can't observe treatment effects at the individual level, what can we do? Well, in plain English, we can say that it's the average treatment effect for people who look like some feature X is what we are looking for, right? So the solution to this is a conditional average treatment effect, which is basically expectation of y of 1 minus y of 0 given some features. Now, these features are what we really care about. So this is nothing but the expected uplift or treatment effect for customers with similar characteristics and features, okay? So by grouping similar customers, we can estimate their expected uplift even though we can't really see individual counterfactual. So that's the key distinction there, okay? So this is very important because we need to really estimate the Kate to really understand what's going on, and then understand the actual or the estimated uplift for any given individual there. Okay, so in that previous table, now we have some numbers here. Now these numbers are actually coming from the uplift model. Okay, these are just model predictions. These are not the ground truth, but they help us identify whom to target. So you can see that previously we couldn't really find out the ITE here, which is basically the estimates for Kate from our uplift model. But here we can, right? Because we're using the same formula here. So y of 1 minus y of 0. So Mr. Grayson was, if you remember, he was a sure thing, right? So we don't get much uplift at all here, right? But then on the other hand, you can see Mr. Drake, who was actually the person we wanted to target, and then he has a quite high of ITE there, right? Yeah?
Wait, so I really want to follow. Where did the y zeros come from? Or so for Mr. Grayson,
Yeah.
Or where did the counterfactual come from?
That's the model. That's the model which is predicting. So I'll go into that later on. But that's actually what is going on. So we didn't have those answers, right? If you remember, we didn't have those answers, right? But now, through uplift modeling, we are going to estimate those values. And that's how we'll get that, okay? And then finally, you can see that Miss Kyle was actually a sleeping dog. She is actually very negative there, okay? So this is the person exactly we do not want to target at all. Okay, so now let's talk about the way we can actually estimate these Kates. So this is coming to your question, actually. So there are actually different methods of doing this, but the ones that I'm going to talk about are actually meta-learners. Okay? So it is a way to leverage predictive ML predictions for estimating the treatment effects. Okay? These are basically, you are using your, your traditional ML models. It could be anything to measure the treatment effect. Really, it could be a neural network. It could be a boosted decision tree. It could be an SVM. It could be anything, right? And also, the predictive model can be a regression or a classification. That's because depending on the problem that you're trying to estimate, this can be different. So in this case, for example, what are we doing? We are just saying that did they purchase or not, right? That's actually a classification problem. But imagine that you had the outcome variable as revenue. In that case, it would be a regression problem. So that is possible. And of course, there are different types of meta-learners here. We have S-learner, T-learner, and X-learner. Now here, for this talk, I'm just going to focus on S and T-learner. Okay? So, all right. So let's go into S-learner. So this is our training data. Let's just imagine this is our training data from the randomized A/B tests, okay, that the team did. Okay? And these are all features. So we have two features, X1 and X2, which is the engagement and the tenure. And then we have the treatment variable, which was the email sent, and the outcome variable, which is it purchased? Okay. Now, the idea in S-learner is that it's a single model for everything. So you train one model on all data with treatment as a feature. Okay. So you combine the features plus the treatment, and then you train the model. Okay. Then you predict both outcomes and compute the uplift. Right. There are some good things going on here because it's a simple technique and it works with limited data really well since it's only one model. But the problem is that it's treatment, they actually treat it as just another feature. So it might not really capture in complex interactions. Plus, if you really have less data with t equals 1, meaning the treatment data, then it might really ignore anything, the model, because this is actually a single model. So the way it works is that we have the first line is just combining the feature and the treatment. So we have the X combined, which combines the feature and treatment. By the way, don't use this code. This is not the real code. I mean, this is I would say a pseudocode or something. I have the real code later on there. So and then you train the model. So the model can be, in this case, it's a light GBM classifier, and then you fit with the full combined features and the treatment, right? Now the third step is where things get interesting, because now, since remember, this is a single model and your treatment is actually a feature. So what do? You actually predict Y1 by taking all the other features, okay, that this person has and just freeze with t equals 1. Meaning you are just saying that when this person is given the treatment, what is actually our outcome? That's Y1, right? And Y0, on the other hand, is actually the same thing, but flipped, meaning when t equals 0, when it's the control group, what should be the outcome? That's the model predicting. Now, the fourth one is that we compute the uplift, which is our Kate here, right? And so it's denoted in literature as tau. So that's why I just put it as tau. And then that uplift is the same formula that we have been seeing throughout, right? Which is y of 1 minus y of 0. Okay? So that's exactly how it's happening. And to your question, this is exactly how we are getting those values, right? So, all right. So now let's look at the T-learner. Now, as the name suggests, so S was for a single model, T meaning two models, right? I say at least because you can have a situation where there are more than one treatment, actually. In that case, it will have each model for each treatment. But in this case, we're just focusing on one treatment, one control. So you have model 1, which is trained on the treatment, right? So remember the training data that we had? We actually split it now. So, split it based upon the treatment that we get. So model 1 gets trained only when t equals 1. Model 0 gets trained only when t equals 0 with no email, right? And this is just a very simple approach, but it can actually do some good things for us. The first thing is that model can now understand different patterns in treatment versus control. It's not just one model you have and then it's getting very fuzzy with what is going on. Definitely, it better captures heterogeneous treatment effects because there must be some other things that is going on. So it just captures it very well. And the best part is that you can tune the two models differently, meaning that there might be a need of a stronger or a more complex model for model 1, for example. Usually that's the case when the treatment is given. And then for the control, you can just have a simpler model, right? You don't need to be so much, that model to be so much complex. But the bad part is that it needs sufficient data in both groups. Okay, that's not. It's not that okay, you have 90% of the data in control and only 10% in treatment. Okay, that won't really bode very well. You need like sufficient data there. So if I just talk about the logic here, right? So it is very similar, but also a little bit different. So the first thing, if you remember, in SLearner, we were combining the features. Here, we're doing the opposite. We are splitting the data by treatment. So we have the X treated, X control, Y treated, Y control, and then we split by recipe. Just imagine that there is a function that is doing that, right? Then on the second one is that we first train our first model, which is the treatment model, right? So that is model 1, and we're fitting on the treated and the Y treated, right? Then we have our model 0, which is we are training on the control model. I just chose a different model here, but you can do anything. And this is just to show that we can have different models here. And then you actually fit it on the control and the Y control, right? Now let's imagine a new person is coming in, okay, where they have their features. We need to predict using both models, okay? Now we do not need to specify t equals 1 or t equals 0, since that was the case in the previous one. Here we have them separate. So all we need to do is y of 1 is we will make our treatment model predict on this, and y of 0 will make our control model predict on this. And then we compute the tau as before. That's it. All right? Now let's talk about evaluation. Okay, and this is where it's really important, just because the traditional ML metrics that we use actually fail for uplift. Now, why is that? Now, traditional metrics like accuracy and F1 measure how well we predict outcomes. But like for uplift, we actually need to predict treatment effects. That's a fundamentally different thing. So a model can perfectly predict who will buy, but completely fail on identifying who will buy because of the treatment, right? So we need some different metrics there. So there are actually different approaches to uplift evaluation. But here I'm going to just focus on one of them, and which I really found very useful from a practical perspective. Okay, so it's called the actual uplift by bin, and it goes like this. The first step is we rank users by predicted uplift score, descending, right? So the best users who are most impacted by the uplift are actually first, meaning you're targeting the quote unquote the persuadables, right? So we have these many users, all right? These are ranked. Then we divide them into bins. For example, a usual case is just divide them into 10 bins, all right? So let's say we just divide them into these bins, like this. Then third step is that we calculate for each bin, we calculate y of 1 minus y of 0, okay? To actually calculate the average uplift in each bucket B, right? So where y of 1 of B is the average outcome in the treatment group and bucket B, okay? And y of 0 is the average outcome in the control group and bucket B. Remember, this is the average outcome, okay? So that's very important. So this tells us if our model is actually ranking high uplift customers at the top. That's very important. So the graph kind of looks something like this, okay? So this is an example of a good uplift model would actually produce a graph like this, okay? So what really is going on is that from the first bins, you can see that the uplift is high, meaning that you get a lot of uplift, and these are the persuadables, right? From those users in bin 1. Remember, these are ranked, right? So in bin 1, we have the highest concentration of users who are most positively affected by our uplift model or by the intervention there, right? So And then you can see it goes down. And that's expected because you actually expect things to go down as you move across on the right side, because those people are not really that persuadable, and they are not going to react that well to those interventions. Okay, so actually, if you look at from bin 5 to 8, they have a negative uplift, right? So these are actually the kind of sleeping dogs we should avoid, right? So the key takeaways from this kind of a graph, this is actually a sanity check for the model. When you're building this, when you're building an uplift model, this is very important to have a sanity check whether you're targeting the right people and have things in order, okay? So in the best case, we expect a monotonically decreasing pattern as we move from left to right. And if uplift rises or stays flat as the bins increase on the right, it suggests that the model is probably overfitting, because it is actually doing pretty well on the training set, but on the test set, it's not really having an effect on those and actually choosing the right people there. So if the early bars are close to 0, which in this case it's not, but imagine it, if it was, then we can say that the model has a weak uplift there. And if less data, then it's much, much better to use fewer bins. Here I used 8 bins just to showcase. But you could start with 10, but if you really have less data, just lower the bins. Otherwise, you will see a lot of noise, meaning you'll see a lot of zigzag pattern there. Okay. So now let's talk about some strategy. So you have your uplift model, you have your graphs. Now let's talk about how would you deploy this in production and how would you target them, right? So there are actually 2 options, or 2 main options, I would say, for targeting. The first one is target all positive uplift. So meaning in this case, it would be bins 1 to 4. So you target those people whose uplift are greater than 0, okay? So then in that case, you have more customers reached, you have lower average uplift per customer, and then you're not causing any kind of a loss to the company, because you're just predicting who will benefit positively from the intervention, right? A more conservative way is actually target only the top uplift bins. Remember, this is so in real data, there is data drift, there is concept drift, so things can change, right? So a more conservative approach is target only the top uplift, meaning target only the top decile, or the top deciles. In this case, it's bins 1 and 2, where you're impacting fewer customers, but they have the highest impact, right? So you're actually playing it safe and making sure that your intervention is actually making any kind of a difference. And it's also better for some resource efficiency. So for my personal use cases at work, mostly, we actually mostly go with option 2. Okay, and have a threshold for that uplift. Okay, so customers above that certain threshold are only given that intervention. Okay, so this is a real example. So I have the code and everything and the QR code later on, but this is a data set which is publicly available. So it's open sourced, and it's basically Criteo is an advertising company which did this trial, and where the target variable is the conversion, where whether the user made a purchase on the advertiser's website, and the treatment variable was whether the user was actually shown an ad. Okay, so here you can see that the S learner and T learner show different uplift plots. The S learner has a high first decile, right? In this case, there are 10 bins. The first decile is high, but then it is not really, there are actually some patches. You can see the last decile is actually also the second highest, which is not really what we want from our model, right? You do not expect the model thinks that the 10th decile are the lowest performing customers, but in this case, it's not. In reality, it's not. So which means that it's not really able to gauge it properly. The T learner, on the other hand, is actually much better, and you could see a smoother curve there. Okay, so yeah, just there. So all right, so let me wrap up with some key takeaways from today. When to use uplift modeling? Well, you can't treat everyone, okay, as I said, right? So when you can't treat everyone and you have a limited budget, you have a limited capacity, that's when you use uplift, okay? And when you think that your treatment has costs, meaning there's time, money, ethical reasons, customer experience, you name it, so it has some kind of a cost when you give a treatment to somebody. In this case, you need to optimize from whom to target, right? Or on the other hand, just stick with traditional machine learning. In cases where you can treat everyone, every possible customer, and you just need predictions, not decisions. You don't care about making any decision out of it. And then treatment is virtually free for the business. I mean, if that's the case, really, you just give it to everybody. Yeah, and some practical implementation tips, like some best practices. I would personally go with SLearner as the first step. Now, T-Learner learns better with sufficient data, but I think SLearner is a good baseline to start with. Then also sufficient samples in both treatment and control data is very important. It's not like you have a class imbalance problem in a traditional machine learning. Here your problem is much more, you need to really estimate the Kate, so you need more data there, right? And then validate with different kind of curves, like the uplift curve, like for example, the actual uplift by bin that I showed, those. And then there are some libraries out there which make things easy for you. You don't have to do them yourself. You have the Causal ML, which is open source by Uber. You have Scikit Uplift. Unfortunately, that doesn't seem to, it is still functional, but they have not updated the library in a while. So I'm not sure about that. And then you have the EconML, which is from Microsoft. This is more for the PhD people. Not really for me. I don't really understand too much what's really in the documentation, but these are really good options to start with there. So with that, thank you so much.
Thank you. Thank you for that talk. That was wonderful. We have time for a few questions.
Thank you for that talk. It was really insightful. Exploring uplift modeling a little bit. Now I want to understand with regards to the data, like data has different distribution and variance. Applications in like marketing or healthcare where like there's a lot of data variance. So how do you like ensure like we get best of the evaluation matrix so as to like basically maintain the accuracy and the reason of the model, like the Gini coefficient it's what is called like. So I want to make sure that I really target correctly, but my data is like haywire. So how do I deal with that?
Yeah, so I think domain knowledge is pretty important here, meaning that we really need to know the right features, which is important for this use case, right? If let's say the same example, the email example, right? If the company has good features on like every kind of customer that they are, so it does not matter how varied these features are, if you are actually having a good chunk of feature that covers most of these, you should be good. But then again, more features meaning more data. And then more data meaning more A/B tests, right? So it's actually a chicken and egg problem. Which is still a research problem. I would say in my company, for example, we are thinking of ways to how do we reduce our dependence on A/B tests, to generate these training data. So is there something heuristic we can do? So it's an open question.
So when you were going over the T-learners earlier, you mentioned that like there's usually kind of like you need sufficient data to use it. Is there any sort of way to determine kind of like how to get a threshold for when you have sufficient data for that case?
Again, that's kind of a very I would say specific problem. It's specific to the use case. I would say number one, if you have too many treatments, you need that much more data. Okay, so not always it's just about one treatment and one control. Okay, you need to have. Let's say you have 3 treatments, meaning you're giving 3 kinds of discounts. Okay, and then you have control. In that case, you would need sufficient data for each of those treatments and control as well. Okay, so from my understanding, I feel it is okay to have the control data to be more and treatment data to be less. That's fine, but it should not be too much over one way or the other. Okay, so yeah, it really depends on the number of features that you have there as well.
And I guess as a bit of a segue on that point as well, in the event that like there is insufficient data, like how feasible would it be to potentially use like synthetic kind of sources to kind of make up for that? Like, would that still be feasible to use those and then run like the T-learning model, I guess?
Yeah, synthetic is an interesting approach, and that's something that that's the first go-to solution that I mean, anyways, anybody goes to. But you need to be careful about that. You really need to be having some good synthetic data along. I mean, you can't just double everything, right? Double or triple the same data that you have, right? One approach could be if you have something like a generative model, let's say like an autoencoder, okay, or like a variational autoencoder, okay. You can actually generate some data to, along the same distribution and sample out of them. That can generate some synthetic data, but I would be careful with that as well. Because usually in uplift model, you're actually dealing with people, meaning these are actually customer data, and customers are very different. So it's not really about some other aspect like an image or something. These are real customers. So real customers have different kind of features. So it is a challenging problem, and I would say it's an ongoing research.
Makes sense. Thank you.
Yeah.
Hi, I really enjoyed your talk. Great job.
Thank you.
You walked through an example where the treatment was binary, 1 or 0. How feasible is this kind of framework for, like, not just binary, but like regression type?
Regression?
Like non-binary features.
Well, I mean, first of all, regression is very, very feasible. I mean, people do it all the time, meaning that you can have a revenue or some kind of monetary value. That's what usually it's about, because you're trying to measure the uplift that you would get by providing some kind of an intervention to the customers, and how much more can you get out of them, right, based out of that. So revenue is a very easy thing, and all you need to do is change the classifier to a regressor, and then it should just work there, okay? Regarding if let's say it is still a classification problem, but it's like a multi-class problem, I would say. That also, in my mind, nothing changes. I mean, if you think about conceptually, like the meta learners, they don't care whether your problem is a binary or not. Okay, if you can just do it well internally, I think that should be good. Okay, it's the treatments that matter more, not the target variable in this case.
Great. Well, let's thank the speaker again.